can get out some more paper, flip paper, keep writing, whatever you're doing, keep doing it. And you probably know from general chemistry, and if you forgot, I'll remind you that water can act as either acid or base. I've never really mentioned this to students before, but now that I think about it in organic chemistry, water is typically going to be acting as a base, but not always. In this first introduction, Chapter 5 to acid-base chemistry, we might also see it occasionally act as an acid. So you'll be prepared for this type of thing. Well, off the top of my head, let's just draw it playing both particular roles. In the last example, we saw water acting as a base. Let's do another example, same one. I'm going to use a simpler acid to draw. I'm going to use hydrochloric acid. This is what my Cl looks like. Okay? It has 3 pairs of electrons around it. And we're going to have water. So this is hydrochloric acid and water. And between these two, which one is the stronger acid? Which one are you going to make coffee with tomorrow morning? Hopefully not HCl, because we won't see you in class. Okay. HCl is a strong acid, and we should just know this from general chemistry. This is the stronger acid of the two, then most likely water is going to play the role of base. Okay? Maybe you won't know that immediately, but you'll learn it eventually. Instead of drawing the conjugate acid and conjugate base, I'm going to practice drawing these particular arrows. I'm not going to explain all the details yet, just a few, but these arrows start from a pair of electrons on the base. They go to a proton, they form a new bond, and hydrogen doesn't want 2 bonds, so the electrons in the hydrogen-chlorine bond will be given back to chlorine. So I didn't draw the products first this time, I drew just the arrows. This is how it works, this is how I know it works, and this is how you'll slowly learn that it works. The base reacts with the proton. The base is the substance that can accept a proton. It does so using a pair of electrons. The acid is the substance that donates a proton. And this is the process. So if we look at this arrow here means movement of these 2 electrons to form a new bond with hydrogen. So let's actually draw what happens, what this red arrow means. First, everything that doesn't change I've just redrawn here. And this pair of electrons has now formed a bond with a proton. I've only drawn hydrogen attached to oxygen because that's what this arrow means, and the second arrow means it's detached from chlorine. We'll keep practicing, don't worry. When we get to the Lewis definition, I'll bring us up to speed on all of this. Let's try, or why don't you try and anticipate, just in the next 30 seconds, draw what chlorine should look like here. What do you think it should look like? How many pairs of electrons should it have around it? It has 3 that we didn't do anything with. This one, this one, this one. Should it have 3 pairs of electrons, 4 pairs of electrons, 2 pairs of electrons? You fill in what you think happens with chlorine. These 3 arrows, or these 3 pairs of electrons were already there, haven't done anything with them. But there was one bond here. It's 2 electrons, and we have a red arrow showing this bond moving towards chlorine. What should this chlorine look like? How many electrons should it have? Another clue, this doesn't look like a proper octet rule for chlorine. The whole reason you spend so much time with Lewis structures and octet rule is so that you can always draw these molecules and atoms properly. Hopefully this is what some of you drew. If you didn't, you're going to practice this lots until you can do it. When water and hydrochloric acid react with one another, hydrochloric acid is the acid, the base is water. The pair of electrons on oxygen accept a proton by forming a new bond to it. Hydrochloric acid donates a proton, and this particular bond breaks. This would be the resulting movement of all these electrons. The first arrow shows the formation of this new bond. The second arrow that we drew over here shows this bond breaking. There's no longer a bond between these 2 species. And it shows the electrons going to chloride and ending up there. Okay, so this is the thing that you have to practice. Let's flip the script here a little bit on this. We're going to show water acting as a base, as an acid. But first, what we'll also label here is this is the strong acid. This is its conjugate base. This is hydrochloric acid's conjugate base. It's missing a proton. Water served as the base here. When we're comparing these two things, we see that water has an extra proton attached to it. We know, therefore, that it's conjugate acid. Okay. Let's do another problem. We're going to switch things here a little bit. I'm going to take a kind of a somewhat exotic molecule here. This is called sodium amide. You don't need to know its name. And you might not know any properties about sodium amide at all. That's absolutely okay. But I'm going to tell you right now that it's a strong base. And that's going to make water, in this example, our acid. Water can play both roles. Water can accept a proton. When it accepts a proton, it's serving the role as a base. Water has 2 protons attached to it. If it can donate one of those protons, then it's serving a role as an acid. And it just turns out that sodium amide is a very, very powerful base. Sadly, I drew these in red, so I'm going to use blue arrows this time. But this blue arrow is going to be the movement of 2 electrons. Notice that it originates from the base, it originates from a pair of electrons on the base, and it goes to an acidic proton. So this first arrow means moving 2 electrons, forming a bond, and accepting a proton. We know that as we form this bond, hydrogen doesn't want 2 bonds. The second bond is going to break and be delivered to oxygen. So these 2 arrows that I've drawn in blue now, the first one means moving 2 electrons, forming a bond. The second one means moving 2 electrons, breaking a bond. I'd like you to just try your best to draw what the resulting conjugate acid and conjugate base of these 2 species looks like in these boxes here. Okay, so just take 30 seconds. Do your best to try these things that I'm guiding you towards. Okay, I'm going to be a little bit quiet here, but not for too long. Again, you should be trying to draw resulting products that result from sodium amide using 2 of its electrons to pick up a proton, and from water, well, hydrogen-oxygen bond breaks, the electrons go to oxygen. What do these species look like? Take a guess at it. I'm not watching you. No one's watching you. Maybe your parents are watching you. Maybe your cat's watching you, but I'm not watching you, so don't be ashamed of whatever you draw. Try to draw something. If you're not sure, you can always make sure it's a proper Lewis structure. If it's not a proper Lewis structure, then you've missed something for sure. Okay, well, this particular compound is serving as a base. It accepts a proton. It's getting a proton from here. It's using these electrons to do it. If you drew something like this, and if it's crooked sideways or some other direction, absolutely fine. But if you drew ammonia, you've got it right for sure. Okay? This is what the base would look like. Or another thing we could say, this is the conjugate acid. This is what it would look like if sodium amide picked up a proton. Well, what's the conjugate base of water? If water gives up a proton, I hope what you had left over here was sodium hydroxide. If you didn't have the sodium here, I don't really care. If you had this hydroxide bit, that's the more important part. Okay? If you didn't have any success on this, practice it. You'll get better at it, but it's not going to happen intuitively. Not everything in science is intuitive, but that's why we practice these things, and you'll get better at them. Okay? So this is just a quick example of water serving as either a base, in this case, where it accepts a proton, and here's its conjugate acid. When water serves as an acid, it gives up a proton, and this is its conjugate base. Again, if you have questions about this that are brewing up in your head, or something's really, really wrong here, or you're really confused, send me a quick chat. But otherwise, jot these on a piece of paper. We'll talk about them in about 30 or 35 minutes after we take a break. We'll have plenty of time in office hours together for me to field questions from you. Okay? Hopefully that makes sense. So this is really where we spend most of our time in acid-base chemistry. We focus on this Bronsted-Lowry definition most of the time, and we're focusing all our attention on this little guy known as a proton. The Lewis definition is kind of confusing, and hopefully in the pre-lecture videos I tried to point out the differences, but that Lewis definition and Bronsted-Lowry definition are usually fully compatible.